thank you for the opportunity to talk a little bit about what we're doing in my lab with diffusion posterior sampling. And I really want to thank tremendously Xiaozhang and Altea Lorenzen, who are here. If you have really hard questions, those are going to be the folks to ask here. But of course, thanks to much of the team and sources of funding. So we haven't done a lot of CT today. Just to get everyone in the right frame of mind, I am talking about the CT reconstruction problem. So we're talking about projection data. We're going to form something like a sinogram, and I want to reconstruct that back into a volume of attenuation coefficients. It's a long history. Probably most of you have learned in your medical imaging classes where you can do filter back projection. When I was in graduate school, I was on the upslope on model-based reconstruction. So even though I'm an electrical engineer, I learned all the physics so that I can put together a good forward model. And of course, now we're in the era of deep learning. Regardless of which of these you want to apply, as soon as we get to the real world, you have to deal with the realities of the real world. Even if you have the perfect detector, you're going to have quantum noise in your data. Photons aren't going to move the way you want. They're going to scatter. You're going to get these additive effects that you have to worry about. And our detectors aren't ideal, that there are potential nonlinearities, there are gain effects that we have to accommodate. So, and this beautiful parallel beam projections, we don't get that in reality. And if you're in my lab, we don't even do circles around the patient. We do these kinds of crazy orbits. So there's all kinds of reasons why filter back projection is painful. Now, I do like model-based reconstruction because we can write down all of that physics. Here's kind of the simplest version of that, where we're writing down Beer's law. We can write down the noise model associated with that. And we can write out things like a likelihood function and have a really well-defined reconstruction problem. And you can do maximum likelihood reconstructions. If you've ever done that, they don't look great, right? They're highly noise magnifying, and we really need prior information in the problem to make those images look good. And of course, we've known that for a long time. Very early on, people have adopted things like Gaussian Markov random field priors to help condition that reconstruction problem. The problem is, if you actually look at realizations of Gaussian Markov random fields, they don't look like patients. They look kind of like what you expect, smooth noise. Now, we can do better with dictionary methods and this kind of thing, build up something that looks like a CT scan, but now we're in this new era. I can get deep generative priors that can really help me potentially with this reconstruction problem. And the one that I've gotten really excited about is this diffusion posterior sampling. I don't think we've seen it presented quite this way today, so I'll talk about my version of it. The prior itself is built upon one of these diffusion models where you have example images that you're going to sequentially degrade with fading the image away and adding noise, and you can define that by whatever kind of F and G functions you want. But you're defining that forward stochastic process, and that defines a reverse stochastic process that you could run. The tricky part of it is, in order to do that, you need that pink function there, which affectionately known as the score function. But that's what neural networks are going to help us learn. And then we can run that process in reverse. And what that allows us is that will generate our samples from that prior distribution. So these are examples, and I think this is it might not be yours, Xiao, it might be Pei Ching's, but this is examples from prior distribution in our lab that we've used in our lab. But this is only a piece of it. I want to be able to do reconstruction. So what people have often described is, let's replace that prior distribution with the posterior distribution. The thing I really want is the probability of mu given y in there. So I want to be able to condition this reverse process on my sinogram data and run that process backwards. Now, you could potentially try to learn this directly, or we could do a little Bayes rule trick, break it into the two pieces. One is that pink term, which I have already trained previously, and this is what I really like about this. I can do that once, and then the other term, the orange term, if you kind of follow the work by Chung and do a little chain rule trick, we can write this down in terms of that likelihood function that I've been a fan of for a long time. The nice part about that is I can do one-time training. I can adapt my forward model, however I want, and run this kind of reverse process to solve hard problems, as I'll show you. So the reconstruction really is a discretized version of that reverse process. And if you look at the algorithms that apply this, they're often broken into these kind of diffusion steps and likelihood-based updates. So when we do that in the lab, I mean, there are a lot of different ways to do this. And if you want to read the details of it, you can see how we're doing it in the lab by these papers by Xiao and Shudong. One of the keys to the way we're doing it right now is you need to be able to, for that likelihood function, compute derivatives. And you can do all the work to do that analytically, or what we've been doing is, thanks to Xiao really, we have a sort of PyTorch compatible GPU accelerated projectors that can use the auto differentiation that's already in there. So I can now make really complicated likelihood functions and just let PyTorch do all the work. We're making this available. I don't have an archive number on it, but wait a couple of days and this will be available for non-commercial use. So let's look at an example of sparse CT just to kind of warm up. I can write down the log likelihood model for this. I have the forward model, and my sparsity is I'm just going to pick 30 frames out of how many ever frames that you would ordinarily have. And of course, filter back projection doesn't look great. It's full of streaks. Maximum likelihood really isn't helping you much. You add a little bit of old-fashioned regularization, looks better. But we can use these diffusion posterior sampling methods, and I'm going to get tired of saying that, so I'm going to say DPS. And they look really fantastic. So I looked at this and said, oh, well, that's great. Let's try to solve some harder problems. The first harder problem that I wanted to solve is it's a version of CT where we use more than one energy in the data acquisition. So a lot of people refer to this as spectral CT. There are a lot of different ways to do that. You can have, for example, you can collect the data at two different tube voltages. So you have a high energy acquisition and a low energy acquisition. There are also ways to do this by having special detectors. You can have a detector that has multiple layers. Again, you get a low energy channel and a high energy channel. What we want to be able to do is to take those now kind of two sinograms at different energies and not reconstruct attenuation values of your patient, but I want to reconstruct two basis materials. I want to reconstruct a water basis and a calcium basis, for example, and I'm not getting attenuation values now, but I'm getting densities, and that is independently interesting to a lot of physicians, right? If I can tell you the actual bone mineral density. So, okay, fair enough, we can do that. I can write down the forward model here. This is kind of a compactified form where we get all of the spectral sensitivities of the system in there. That is, what's coming out of the X-ray tube, how does the detector stop those X-rays as a function of energy, but also the different materials in there. How are they attenuated differently? And I want to see how far can we push this? Can we do diffusion posterior sampling in this case? Well, you can, but I need a new model now. I don't want a single attenuation model. I need this kind of paired data model. But other than that, it's exactly the same. I can go through lots of samples of paired water and calcium bases, build up this prior distribution, and run DPS. And so I apologize to Dan for not magnifying my images as much, but what you're seeing here is the standard compared to lots of different things image. On the left-hand side is kind of the filter back projection of spectral CT. And that is, you take each energy channel independently, do a filter back projection reconstruction, and then in image domain, the image domain decomposition, IDD, is kind of linearly trying to invert those forms. And both those steps are noise magnifying, so you can see that in the data. You look at the next column over, the model-based reconstruction. You know, we do a lot better with reducing the noise, but there's still a lot of stuff in there that is making us hard to see what's important. In the middle, we have a couple of competing methods. Spectral DPS is in that second to last column, which is starting to look really good compared to the ground truth. And again, I think you could argue that, you know, maybe we perform a little bit better than these other competing methods. Maybe it's kind of the same. It really depends on the case you're looking at. The nice thing, again, is I can change my forward model. I can change my likelihood. I can go down to this KV switching problem and use the exact same methods. All I've done is change that likelihood function. So I've gotten really excited about this. But let's make it harder. Let's think of the case, particularly in those bottom images you saw here. When I do that material decomposition into water and calcium bases, what's all that stuff in the middle? All that stuff is actually iodine contrast agent in the heart. It's got to go somewhere, and it's going to end up mostly going into that calcium basis. And that's good, but what if I want to see that independently? What can I do? Well, I'm going to need to make more measurements, probably. And maybe I can do that with some of these new photon counting CT systems that are out there. They have an ability to set thresholds to say, well, as I count these individual photons that come in, can I tell you what the energy is? If it's below this, I'll put it into a low energy bin or a middle energy bin or a high energy bin. Now, of course, it doesn't do that as perfectly as we want, but a reasonable model of that system sensitivity is shown here, where you can see, even though I have these two dotted line thresholds, there's a lot of overlap. So that's in part what makes the problem hard. There are other things that make the problem hard here as well, and I'll talk about that in a second. But the physical model is really, it's the exact same thing as we had in that two material case. But just like the two material case, if I want to do this, I need to now train a new diffusion model with triplets of data. And this is something we've done in the lab, and we're running that reverse stochastic process with a triple of sinogram data. And we've tried this for two different contrast agents. We tried this for iodine, which is kind of the standard thing that you would do in CT. And this might be the case of pushing things a little too far, at least for the particular set of thresholds and photon counter that we've done here. While you can see that we're doing better than that image domain decomposition with spectral DPS, we're starting to look a lot like the ground truth, but there's still a lot of bone, for example, in that contrast image on the bottom, right? And the reason is, atomically, kind of iodine and calcium are not so far apart. It makes that decomposition really, really tough. So we've also looked at gadolinium. So gadolinium generally isn't a CT contrast agent, but because of the way gadolinium attenuates as a function of energy, it becomes a lot easier to pull these apart. And we've been able to have some success here on the right-hand side doing that harder decomposition problem. So that's all well and good, but everything I've showed you so far is still pretty idealized. Let's think about, you know, maybe where the rubber meets the road a little bit more in terms of what's happening with photon counting detectors. There are a lot of non-idealities in these that make things a lot more difficult than you might start to realize. There are things like charge sharing. When photons come in and interact with a pixel, the charge doesn't necessarily all stay in that pixel, which means you're not going to really get the right kind of energy discrimination there. It's going to distort your spectral sensitivity. There are other things. If these photons come in too quickly, and you know, each time one comes in, we get a little pulse, and that's how we're getting our energy information. If a bunch come in kind of simultaneously, that's going to distort that. It's going to appear as higher energy. So we want to see what can we do when we have this more complicated data. Now, really thanks to Ken Taguchi, who's got an awesome toolkit to simulate these kinds of things, we've started making data that looks more realistic, talking about how big is that charge cloud, or when we set a threshold, how much variability is in there. So we've looked at that, and we've looked at that in data where not only is that not ideal, but maybe it's changed from when we calibrated the system. So if anyone out there has a photon counting CT, you know that there's a pretty strict calibration process, and things like temperature changes can make things change. We're going to model some of that change by just adding some randomness to those parameters. And if we do that, I think, yeah, this shows up reasonably here. You can see what happens is you get a little bit of kind of pixel-wise mismatch in kind of what you're expecting. These appear as kind of vertical streaks in your data. Now, you could go and try to gain correct that out by doing an error scan, and you would kind of correct it, but the problem is you haven't corrected the spectral part of it. The spectral sensitivity is not really modeled there. So we want to see how can we tolerate that kind of data. Let's consider the case where maybe I got that mean spectral sensitivity all right, but we know there's something not quite right about it. And I want to change my problem a little bit so that that spectral sensitivity term, that S that's in here, instead of saying that that's fixed, let's say I kind of know the mean of it, but there's something else going on because I know the temperatures changed and the thresholds moved around. I want to model that change not by doing the complicated thing that Ken has done with his toolkit, but let's do something simple and just say there's some additional filtration on that pixel. And it's unknown, and I'm going to try to jointly estimate that unknown filtration as well as the material decomposition. So I'm now jointly estimating these kind of odd spectral distortions and my material bases. So what happens when we do that? Well, when we do projection, now there's another way to do a spectral CT, which is to do the decomposition first and then reconstruct the two material channels. That's what was done in this case. It's similar to the kind of image domain in kind of appearance. There's a lot of noise magnification there. What is hard to see in that is what we see when we do spectral DPS without any sophisticated calibration. What you'll see is there's a bunch of ring artifacts there that appear in both channels. Whereas if we do the joint calibration, give the model just enough room to kind of move those spectral sensitivities around, we can do a lot better. Maybe there's a little bit of residual in that calcium channel, kind of in the middle in the cardiac region. But again, I used a pretty simple model, just a little bit of filtration there. We could probably advance that and do better. So this is hot off the press work that really Xiao has done in the last 2 months, but I wanted to show it. Another real hard problem that we have in CT data is scattered radiation. There are all these X-rays that aren't cooperating with us, and they bounce around, and if they don't go to the detector, that's fine, but if they go to the detector, that's corrupting our underlying data. So there's this additive term in our forward model that you can go to a lot of trouble. You can perform Monte Carlo simulations and try to get at that. But I thought, well, what can DPS do for us? And let's do the same thing. Let's write down that forward model and say, I'm going to come up with some relatively low dimensional parameterization of the scatter. In this case, you can think about the projection data that I'm getting. That sinogram I have has an additive sinogram to it, and there's a different one for each energy channel that I don't know that I need to estimate, and I want to estimate that simultaneously. So the model we've chosen here is to say that each row in your sinogram is a scaled Gaussian model, so each has 3 parameters. So 3 times 2 channels times number of angles. It's, you know, it's a bunch of unknown parameters, but not certainly much smaller than the parameters built that are making up the soft tissue and bone basis. So let's give that a shot. You have a ground truth image on the left. The middle image is, we're going to again do spectral DPS with no scatter estimation. So here's a case, deep learning isn't going to bail me out from not getting it in the model. You can see that there's systematic underestimation, particularly in the middle, the cardiac region for the water channel, and there's overestimation in the calcium channel, whereas that joint estimation model, we're starting to see the features that we really want to see. So in this case, you know, those major vessels in the middle. To illustrate that a little bit better, here's a difference image that really kind of highlights that over and underestimation there. And whereas the joint model is allowing us to accommodate that. Now, the other thing we can do, because this particular data was done in simulation, we made the ground truth scatter with a Monte Carlo method. So how did we do in our actual scatter estimates? Well, I mean, within the simplicity of the parameterization we picked, which is these kind of single Gaussians per row, it looks pretty reasonable. Could we do better? Yeah, maybe, but we're also making the problem bigger and more complex. So an astute observer would say, that's not actually real data, Webb. Well, okay, let's do this on real data as well. So this is going to be applying exactly what you just saw to phantom data in our lab. Now, okay, so everything I've showed you up to this point, at least all of the cases where we were doing the 2 material basis problem, that was the same underlying diffusion model trained on human data sets. I'm going to apply that here to this lung phantom, which is sort of human looking, realist, but so there's some additional mismatch there potentially. When we do that, on the left-hand side, you can see when there is no scatter estimation, we see the kind of classic shading artifacts. It's a little bit hard to see the kind of cupping in the middle, but you can see some of the classic shading artifacts there. In the joint problem on the right-hand side, a lot of those scatter effects have gone away. And we know this phantom is uniform. That's uniform tissue equivalent plastic. The bone is bone equivalent material. So the decomposition is working out pretty well, despite this not really being human. So I think this shows some of the power of these diffusion methods where we're constrained to our data, right? But we can leverage these strong priors. And we can look at the scatter estimates as well. So I didn't say this, or it was on the slide, but I didn't say it out loud. That data acquisition we did, because of the size of the phantom and the size of our detector, we actually did an offset data acquisition. So, and you can see that in the scatter. You can see the offset in the scatter estimation. It's not symmetric. And you see it changes as we spin the, in this case, spin the phantom around. So that looks reasonable. The other thing that's interesting that's in there is you can see a high frequency kind of banding effect. And that's actually real in a sense. We know that our X-ray tube has a high frequency variation in output, and it's showed up in our estimates as well. So again, that kind of builds confidence that this is doing good things. In any case, that's really what I wanted to talk about, just to talk about some of the hard problems we're trying to solve in our lab. In terms of a summary, again, there's no reason to throw out all that wonderful physics that I've learned, and we can still do deep learning. Things about diffusion posterior sampling that we like are this ability to do one-time training, making sure our reconstruction is constrained to fit the measurements, and to solve these things that if you asked me a couple of years ago, it's sort of doing the reconstruction problem and system ID simultaneously, that we can solve some of these is really great. Ongoing work, we're trying to figure out how to scale all of this work up to kind of intrinsically 3D models. That's tricky for a lot of reasons, but we have some ideas on that. You can read about it. And we're looking at applying this to more physical data, novel systems, and looking at other forms of this kind of difficult joint estimation, kind of doing the system ID and reconstruction at the same time. So I will stop there, and thank you so much for your attention.
Thank you so much for this great talk, Webb. I have a question on the forward model of the scattering in the CT. So it seems that you formulate the scattering as an additive term. I'm wondering if there's like a more complicated way to incorporate the scattering into the forward model, or like it's quite standard to just consider scattering as an additive term.
Well, I picked that model because that's the model I believe in. I think people generally, when they think about X-ray CT, you think about the primary photons are the ones that go straight through and arrive at the detector. So what is the other photons, the secondary photons, are kind of additive in that sense. But I think it's absolutely true that you can come up with a much more sophisticated model for the parameterization of that scatter. I mean, we've done kind of the most simple thing with Gaussians. I know there's other work out there. And we've looked at that a little bit. It turns out if you make that model really, really complex, it can make the joint estimation a lot harder. So one of the reasons why we simplified it for that problem, we simplified it for the kind of spectral distortion problem, is if you make that too difficult, it becomes challenged to get everything to estimate simultaneously.
I see. So a quick follow-up question will be, because you consider scattering as an additive term, so you can perhaps use my PhD advisor's restoration prior to regularize the problem. Is that, that's just my thought.
Yeah, I agree, and I like DPS. I'm not wedded to DPS. I know they're emerging things that are faster, better. I also want to talk to Beck about how do I train with data that has blur and stuff in it, and to build up a nice prior model when I'm not starting with ideal data, right? I mean, everything I've done here, I trained with CT scans that already have noise and blur in there. How can I move away from that? So
yeah, it's a great talk. Thank you so much.
yeah, thank you.
So there's a question from Bruno Demont. Very nice work. How do you obtain the high quality basis material images to train the spectral DPS? And can the DPS ever generate better images than the ones it was trained with?
Well, I'll answer the first question. Is you have a really great grad student like Xiao, who has figured out how to take some online data sets, and through really kind of a series of operations. So we were looking at single energy images that we've done some soft thresholding on to figure out where the bone is. We've done a little bit of kind of morphological operation to figure out where the contrast is in those scans. So we have a process for doing that with real data. Now, there are some limitations to that. There are things that are not going to be in those data sets. Things like calcifications in arteries that are going to be trickier to get at. So we're thinking about that, but there are limitations, and I forgot the second half of that, Xiao. Or
yeah.
Can it be better?
Do you think the DPS
I don't know.
generate better images than the training data set?
I don't know. I'd be tentative to advertise that you can be better than your training data. I mean, what have we added? I mean, we have the measurements, right? So if the measurements support something that's better than the training data, I suppose it's possible. But I don't know. That's not my goal yet.
Yeah, thanks for a really, really interesting talk. I wanted to hear your thought. So the DPS introduces pretty strong prior, right? It's a generative model. And in this context, you have a hard tomography problem. So what do you think is it better to have a very strong prior in this case, or much more accentuate the physical aspect? And it's related to previous case in the sense that you can do very accurate forward modeling, or you could say, you know what, I'm going to push it all to this DPS-based diffusion prior to fix it up.
Well, so I want to be careful here, right? So I showed you examples where if I don't try to fix the data, and I just say constrain yourself to the data, but use this sophisticated prior. We saw those artifacts. They show up, right? What I'm suggesting is even if I just give the overall algorithm a little bit of room, even though I have the wrong kind of spectral distortion, even though I have the wrong model for scatter, giving it that little bit of room kind of lets you. I mean, in a way, those things are nuisance parameters that if I can use prior to push that out, that's a good thing. Now you're suggesting maybe I don't need as big a gun as a diffusion model to do this. Maybe.
No, I'm more curious as to your thought about it. Maybe you do need it. It's fine.
Well, we did start with just kind of pure model-based approaches and more classic. I heard handcrafted priors. I think it doesn't work well. It doesn't work well in those cases. So.
Thank you.
So one more online question. Is the three material DPS enough to do the three material decomposition, or you need to add a additional constraint to do the decomposition? And how many time steps you are using in each diffusion sampling?
So are three materials enough? Well, we saw in the case of iodine. I mean, in terms of the problem identifiability, you would think three are enough, right? You need to make at least three measurements to get three things. We saw that even when that's the case, that doesn't necessarily save you in the case of iodine and calcium. Now, there's a lot of work out there that is suggesting maybe I don't even need three measurements to estimate three things. There are folks that are trying to make multi-material decompositions from single energy images, so maybe that's possible. One way to do that is to suggest that there are constraints when you're doing reconstructions. There are volume constraints that you can apply to help you. That's not going to work everywhere. That would only work in regions where everything adds up. If you're in the lung, that's not going to work. And what was the second one?
How many time steps?
So I'm gonna do a sort of a soft punt on that question, in that we're doing 1,000 time steps. I'll say that. However, if you read some of the work we've done, there are ways to cheat where we jump ahead a number of time steps to make things much more computationally efficient. So the answer is the diffusion model has 1,000 time steps, but we're actually doing much fewer than that to make things computationally tractable. So, and if you want to know more, the paper is referenced in the middle of the talk.
Another short question. What hardware are you running this DPS code, and how long does it take to do a reconstruction?
We buy a lot of gaming GPUs in my lab, so we have I think coupons for all the latest games. But these are I think most of this was done on whatever the latest, the 4090 RTX, I think is what we're using for most of this. And timing wise, I don't know, Xiao, what's the time for
for the single energy reconstruction? I think it can be done within seconds, and for the material decomposition, it's about 5 seconds per slice.
It's quick. For the 2D problem, to be clear, as we scale up to the 3D problem, it's a lot more challenging. So my time has to be up, right? Thank you.